I think it's time to begin. Our next speaker will be introduced by Professor Dan Debray. Dan?
It's not often you have the opportunity to introduce a friend that you've worked with for nearly half a century. When Francis first came to Stanford University in the early 60s, I was still working at Lockheed, though I had the association with Bob Cannon up here completing my graduate work. I originally thought, oh well, here's somebody else who's going to be working on the physics side of things. But very clearly, after our first couple of meetings, Francis was asking questions that had a lot to do with questioning the validity and the basis of the engineering that we were hoping to provide transfer of some of the technology from Lockheed up to the planning of the wonderful program called Gravity Probe B that you all know about. Francis came from having finished his doctoral work in the University of London with Professor Blackett. He worked on Earth magnetism of rocks. You understand immediately how that transfers directly over to the technology for a Gravity Probe B experiment. And I think that it's important to understand that the person you're going to hear from has that kind of breadth that would step with the educational experience rather than the training associated with one field into another with just the intellectual growth that goes from making these transfers. And in each of the areas that he has been involved in over the years that I've worked with him, I've admired the ability as a science historian in writing a history of Maxwell to his ability to know the catacombs of Washington, D.C. inside out, the excellence that he brings to each of the things that he puts in effort from. As the principal scientist of Gravity Probe B, he's going to tell you a little bit about the empowerment of that experiment as a result of being here at Stanford. Francis Everitt.
Here is a nerve-wracking moment in the history of a physicist when there is the apparatus going up and you're used to twinkling with your apparatus in the lab, but the closest it's ever going to be to you again is 400 miles away. That's at Vandenberg Air Force Base. So Gravity Probe B is an experimental test of Einstein's general theory of relativity, initially suggested by Leonard Schiff, and it consists in putting a gyroscope in orbit around the Earth, and then there are two effects which cause the gyroscope to precess, even if it's an absolutely ideal, perfect gyroscope with respect to a remote guide star. And there you see the two effects, one of which is called the geodetic effect, which is due to the curvature of space, and the other, the frame dragging effect, as the space drags space and time around with it. The basic formula was derived by Leonard Schiff. There's a little correction because the Earth is oblate, and I learned quite a lot through this one. By the way, we have a color code here that the blue means a student, and the green means non-student. So Dan Wilkins was the first person to work out the oblateness correction, and it took him about 30 pages, a very careful, elegant work, because it's much more subtle than you would think. At a certain point, I showed this to John Breakwell. And some of you know John Breakwell, and he's looked at this and said, came back the next day with the whole problem solved in a more elegant way in 3 pages. But still, that's why physicists have to learn from engineers. So the experiment then consists of a telescope and actually 4 gyroscopes. And they're going to go in orbit, polar orbit around the Earth. And that's the moment of launch. And you start with a gyroscope the size of a ping pong ball, and look what you end up in the middle. That's the spacecraft on the launch tower, and there's some human beings to just give you the scale. And so we go on and launch. And here is the data from 4 different gyroscopes. And if Newtonian gravity and space-time were correct, there would be a straight line along the top of each of the graphs. Instead, you see there's a slope, and you're seeing general relativity straight there in the raw data. You'll also notice in the red raw data there's some wiggles, and we'll come back and talk about the wiggles later on. Now, this has, right from the beginning, been a partnership between physics and what we call HEPL. HEPL originally meant the High Energy Physics Laboratory, and then at a certain point, rightly, it was renamed the Hansen Experimental Physics Laboratory. It might possibly really be renamed the Hansen Engineering Physics Laboratory. And it's been a wonderful example of Stanford interdisciplinary things. And there you see right from the beginning, Bob Cannon was involved, and then Dan DeBray came on board. And I remember Cannon saying to me, there's this very good man, DeBray, coming along. You'll enjoy working with him. And I found after a couple of meetings, in fact, after the first meeting, that that was true. And one learns the way forward. Then other people came along. The development of the gyroscope right from the beginning was collaborative likewise. It's been an amazing student involvement. So far, we've had at Stanford 83 doctorates, 29 in physics and applied physics, 53 in electrical engineering and mechanical engineering, and the majority of those, by the way, were in AA, and one in the maths department. And the one in the maths department was not about relativity. It was about helium tides in the Dewar. So even mathematicians do engineering from time to time. And there have been 13 doctorates at other universities. And the other enormously impressive thing is what undergraduates can do. So my moral at the bottom is engineers as physicists and physicists as engineers. So, what is the challenge of doing this experiment? Well, challenge number one is you've got to make a gyroscope that's 10 to the 7th times better than the best model inertial navigation gyroscopes. You've got to make a telescope much better than the best prior star trackers. Somehow then you've got to process the data from them and get an honest gyro readout calibration. And it turns out we do this by a combination of space and cryogenics. And there you see on the left the payload, which consists of a telescope, 4 gyroscopes, and a giant thermos bottle or Dewar, which contains 2,420 liters of liquid helium at launch, and which came cold for 17 months and 9 days in space. It's a pretty big thing. It's about 10 feet long and about 8 to 9 feet in diameter. A little calculation with the latent heat of liquid helium. The total input into the Dewar of that enormous thing is about 130 milliwatts. That's the 30th of the amount of heat put out by a flashlight bulb. So it was a remarkable piece of engineering by Lockheed, whom we were all the way through collaborating with. What has been the areas of the major student involvement? Basically everything. They were involved in the gyroscope, all aspects of it, in developing some ultra-low magnetic field technology. You will soon see why we need that, even in developing the Dewar technology, and so on down through the rest. And last, and by no means least, on-orbit operations. So what does a gyroscope look like? A gyroscope is a sphere the size of a ping pong ball, round to 30 micrometers, no, excuse me, much better than that, 10 nanometers, and you can translate that into microinches likewise. We ended up with a design which would be electrically suspended, spun up initially by gas, read out magnetically, and operating cryogenically. Now, to develop a gyroscope that's 7 orders of magnitude better than the best before, you have to make a lot of things nearly zero. You have to make a very homogeneous and very round rotor. We have to make the spacecraft drag-free. I'll come back, of course, and talk about that. You have to work in very low magnetic fields and at extremely high vacuum, very low pressure, very low electric charge on the ball itself. And all of these technologies, which are just sketched there, are part of it. Notice that I have a little thing at the bottom. The electric dipole moment has to be very small, and this turned out to be an issue for a curious and interesting reason. So now here's a piece of high school physics, and I won't go into it in detail because you could do it yourself in a couple of minutes, but the point of this is to show you the problem, the fundamental problem. So we have a very round, imagine we have a perfect sphere, which, however, regrettably is made of a material that is not quite perfect. So it's slightly inhomogeneous, and it's got some lateral acceleration. Then you'll get a torque, and the gyroscope will precess. And you better have no effect that's going to dominate the Einstein effect or be comparable with that. So you can get a criterion out of how uniform this will get to be. And supposing you were to do the experiment on Earth, you'd have a rotor that was homogeneous to a few parts in 10 to the 18th in density. Even in a regular satellite where you get typical accelerations of 10 to the minus 8 g, it's still exceedingly difficult to imagine. But when we come to the drag-free satellite, which I'll be talking about as we go on, finally we can do it. So let's talk about making a sphere. This sphere, which is in the Guinness Book of World Records as the roundest sphere, was manufactured by this rather interesting machine there. Later, Dan Debray developed a further refinement of it, but it's a lapping machine. And I won't go into the details, but we have self-aligning laps and uniform rotation, and then you reverse directions every now and again. You have to think about controlling the pH of the liquid, which is the grinding, and so forth. This was invented at NASA Marshall Center in Alabama, eventually transferred to Stanford, and there we go. Interesting game, just making a sphere. When you've made the sphere, by the way, you have to coat it very uniformly with a superconducting metal, and that is, which I won't go into, comes next. And then you have to measure it, and of course one of the things you learn all along is it's one thing to make something, another thing to prove you've actually made it. So here is a Talleyrand roundness measurement machine, which was certainly then and possibly even now the best, most accurate roundness measurement machine, which made great circle measurements, and we eventually figured out how to turn those into contour maps. And here's a bunch of students, mostly undergraduates, and you see the names and where they came from. And there is a map. If you were to blow the sphere up to the size of the Earth, the highest mountain would be maybe about 7 or 8 feet in the deepest ocean. By the way, let me tell you something about physicists. When a physicist shows you some data and he says, this is typical data, what that actually means is it's the very best piece of data that he ever got. So that's a typical sphere. Now we get up into orbit, and I'm not going to tell you the details, but there you are. We are able, on orbit, to do one thing we knew we could do, which was determine the difference in moments of inertia, delta I over I, of this very uniform sphere. One thing which was cleverly figured out on orbit as to how to measure the mass unbalance. And we made pre-launch estimates of that. And then you see below the on-orbit data, and you notice the on-orbit data is better. This actually may be partly because the mass unbalance is the maximum distance between the two, but when you spin it up by chance, you may be spinning up about some other axis, and so that it tends to average, but it may not be totally that. So anyway, that was a relief. The pre-launch estimate met the requirements, and the on-orbit data more than met the requirements. Fine, but now we have to suspend this system. And of course, the idea of the electrically suspended gyroscope, which goes back to Arnold Nordsick in the 1950s, was one that eventually we adopted and was very good. And this gives me a story I want to tell you about the relationship between academia and industry. There's a very obvious but not quite true statement you can make, that what you ought to do is go to industry, to the things that industry already knows how to do, not be so foolish as to redevelop them for yourselves, but when you come to other things that they don't know how to do, then maybe you can contribute something. That's true, but it's not the whole truth, because we went obviously to Honeywell to buy the appropriate suspension system, and it worked perfectly well, as it would expect it. It was one, however, that didn't do the trick for us, and we had to redevelop our own suspension system, because that suspension system designed for one kind of electrically suspended gyroscope didn't work for ours, because it interfered with the readout. Look at all the names of the students there. I won't go into detail, but AA and EE students were all involved, and we went through different stages, first going to an analog ground-based version, a digital ground-based version, and finally to the digital flight version. Let me just say this about the digital flight version. You have to be able to suspend over a range of 8 orders of magnitude. You have to be able to support it on the Earth, then you have to be able to deal with various situations on orbit, including accelerations from micrometeorites, and then you have to go back to the operating conditions. And the reason why you can make so much better a gyroscope on space is because you can switch down the support voltage. On the grounds, with our gyro, you need 700 volts. When you go up into space, we were running most of the time at 0.2 of a volt. Except what happens if a micrometeorite hits the satellite? You'd better switch up quick, because you don't want to drop the ball. Or when you have a soft computer failure, and all these things entered into it. But this work, led by Bill Benzie, a former student who is then evolved into the GPB program manager, following Brad. That was it. And here is the moment of suspension, the first time with a backup analog suspension. That's 30 nanometers, micrometers, I mean. We levitate. Notice that after 6 seconds you switch it off and everything works. It bounces. Galileo is right. It bounces in a parabolic path. But now we come to the fact that I said we needed not only to be homogeneous, but to be drag-free. And there we are. So what is drag-free? Probably everybody knows. You have an object inside the spacecraft. The spacecraft is subject to drag. The object is not. So it tends to follow an ideal gravitational orbit. You sense its position and exert force on the spacecraft to make it chase after the object. And the object in this case was a gyroscope, one of our 4 gyroscopes. And on the top right, you see the signal of acceleration before you switch the drag-free on that gyroscope. As soon as you've got the drag-free on, the acceleration is compensated. And those, by the way, are the gravity gradient acceleration initially acting, because it's not quite at the center of mass. And the end up is the cross-track average acceleration was 10 to the minus 11 g. There again, you see the names of 3 students who were critically involved in this process. Okay, now we've talked about having a suspended gyroscope. We also have to do something rather significant. We have to spin it up. Now, if you think about that for a minute, you realize you've got a remarkable problem. Because the whole idea is to make a gyroscope which has absolutely no disturbing torques on it. But you're going to spin it up. And how do you spin it up? By you put a torque on it. Trivial calculation you can do in literally 2 lines shows you have to switch the spin-up torque off by 14 orders of magnitude. We worked, Dan Bracken, the student working with me, with Don Baganoff in the Aeroastro department, and I'm not sure we could have done it without him thinking out what needed to be done. And we end up by running gas through a channel, and then around where the electrodes are, we have a much higher vacuum, and you have to make all the right sonic conditions in the channel, and finally you end up by quite a nice spin-up system. And at a certain point, right at the end of the calculation, Dan Bracken and I asked ourselves the question, well, how big a pipe do you need to take out the residual low-pressure gas? A little calculation, you know, plug it in, about 8 inches in diameter. And eventually I came from this beautiful quotation 10 years later, after we had rediscovered it, from one of the old steam locomotive engineer designers who said, any fool can get the steam into a cylinder, but to get it out again afterwards, that's the challenge. And the reason is, of course, you're getting it out at much lower pressure than you put it in. Same applied to GPB spin-up. Okay, but now we are on orbit, and you see that student, Robert Bromley, in the middle, looking very intensely with other people and looking over his shoulders. He's the guy in charge of the spin-up. And it's an impressive aspect of Robert Bromley that he had the nerve to do this. And then when we spin it up, and you see it taking about 3 hours to spin up to its full speed, or the full speed we took it to, eventually you have to, and Bill Benzie's thesis was involved with this, how do you torque it into the exact right position? Oh, you turn on the biases in the suspension system, and those are things you'd also better be able to turn off again afterwards. So, finally we got it spinning, isn't that nice? Except, here's the following problem. This is an ultra-high vacuum system. What is the one thing anybody who knows anything about high vacuum system, ultra-high vacuum systems, is once you've got the ultra-high vacuum, never, ever, ever introduce gas into it. Except that we are spinning it up by introducing gas into it. So what you have to do, you have to bake it out. But now you need to make an engineering mental transition to the low-temperature physicist's world, because baking out consists in raising the temperature from 2 Kelvin to 6 Kelvin. And doing that for a few hours, and then letting it come down again. By the way, then you have a huge cryopump to suck out the baked-out gas. And there before you, in the left-hand column, you see what the spin-down rates were right after spin-up. Still not so bad, 50 years. But we went on, after the bake-out, for gyro number 4, it was 25,700 years. And remarkably constant these were. Now, when you see all this, and you're first of all very happy about this, and you're watching every day, for about 4 months I looked at all of these numbers, and at this point we had some reason to think again, and it's curious that gyro number, you would think at the ultra-high vacuum everything should be more or less the same spin-down rate, but you notice that it isn't the case, and that actually turns out to be significant. Fine, now we have a spinning gyroscope. You've got a perfectly round sphere, almost, and it's spinning, and you've managed to spin it up and it's nothing else is interfering. How do you measure the direction of spin of a perfectly round, perfectly uniform sphere with no marks on it? Here we come to something called the London moment. A spinning superconductor develops a magnetic moment aligned with its spin axis, and so it acts as a magnetic pointer. And there you see some of the details, and I'll go on, but some very key students here. Greg Goot turned out to be a very important electrical engineering student at Stanford in getting this going. And we'll now go on and see some of the history of this one. So on the left you see a doctoral dissertation from the year 1965 by Maurice Bowl at Stanford, which was the first detection of the London moment. and that curve on the bottom line shows it spinning first one way and then the other way. You should really fold the bottom half over. And so you're measuring it to about 10 degrees, 10%, which means you haven't got much of a gyro readout there yet. So we went on and did a laboratory demonstration with a real gyro, and you're seeing that. Maybe I have a pointer. Let me show you that just for a second. This is looking down from above on an electrically suspended gyroscope in the laboratory, and because you had to have high gas pressure in to get some of the heat out, it's slowing down fairly rapidly. It's also horribly unbalanced, but it runs round in a spiral and finally comes in there, and it's processing at about 300 degrees an hour. So it's a horrible gyroscope. But this was a great moment. I think Winston Churchill said at a certain point in World War II, we've reached the end of the beginning. And this, after quite a few years' work, was the end of the beginning. And there were 5 major developments we had to go through in order to get from there to a flight unit, which took quite a few years, which also led us to the business of a niobium bird. Everybody knows what an iron bird is, right? It's the ground-based model you make of an airplane, where part of it's real thing and part of it's computer modeling. A niobium bird is obviously what you have for a superconducting gyro readout based on niobium. And we had these students. This was Brad Parkinson's name for it, which was a great name. Okay, and now we're on orbit, and we got a gyro readout for 4 gyros, and these are the final resolutions of the readout. This doesn't mean to say the performance of the experiment yet. In the milliarc second per year level, when you're trying to measure 2 effects, the larger of which is about 6.6 arc seconds, 6,600 milliarc seconds. And we are actually achieving the various requirements so far. But you'll see there's more to this story than that. But this gyroscope has to go in an exceedingly low magnetic field to work. Another PhD thesis, this time from Blas Cabrera, who, by the way, is now the the chairman of the director of the Hansen Experimental Physics Laboratory, who developed a way of making very low magnetic fields. And the method consisted in having a closed-up superconducting lead bag and then expanding it, and that pulls the lines of force apart. And this method really works, and we got a very low magnetic field, and in fact, there is looking down into our flight duo with a very low magnetic field in it. So here again is a picture of the duo. Here it is under test at Stanford, on the campus in the Hansen laboratory. Here were some of the dissertations that went into the duo work. And finally, this was our final moment at August 2002 at the ground testing. And this is a nice moment in the life of a physicist when you see your $300 million apparatus swinging from the end of a string. But this duo enables you to do some things you didn't at first expect. And one of the early discussions Dan Debray and I had was, how are we going to point the spacecraft? How are we going to control the drag on it? How are we going to compensate for the drag? And Dan did various calculations, and it dawned on us, maybe we could use the boiling off helium gas to control it. And then Dan did a nice, interesting calculation on the Reynolds number of that gas. And the Reynolds number coming out with the nozzle that we had was 10. The Reynolds number of 10 means that the gas is flowing like honey. Dan made a phone call to a friend of his who knew all about thrust and said, you know, I'm worried because we got a Reynolds number of 10. And the man said, oh, it's no trouble, Reynolds number of 10 million, that should do just fine for you. No, Dan said, no, I said 10. So that led to John Bull's PhD thesis, because the question was, can we get the thrust? And there you see that actually, in fact, the specific impulse is really very good, almost to the theoretical limit. And it was a beautiful piece of work. And then there was further work by other students, including, finally, when we put it at Lockheed Martin, on site at Lockheed Martin was another student, Yusuf Jaffrey, working with them on calibrating the flight thrusters. But we aren't through with everything that we need to worry about yet. Because what about this magnetic story? Well, we have to make a probe that has to go into this very low magnetic shield in the dewar. That probe has to be non-magnetic. Otherwise, you'll just carry a magnetic field down in there. And Dick Parmalee, who was the dewar designer at Lockheed Martin, a terrific guy, said in the end that 30% of the cost of the probe went into meeting the magnetics requirement. And this had to be a detailed collaboration between on-campus people at Stanford, led by John Mester with Jim Lockhart, including a student, Mark Sullivan, who is now the chairman of the physics department at Ithaca College, where I won't go into all the numbers, but we had to take coupons of every material going in there, measure the magnetic fields, and put them in and see whether they were okay. So it was a very intense part of the industry academic collaboration. And we're still not through, because this non-magnetic probe has to go down into a dewar, and that dewar is cold because it's got a lead bag in it, and you're going to put a hot probe into a cold dewar. That's a really interesting thing to do. You had an airlock in which we connected it in, pumped out the air, refilled it with helium, and then went through a process of reassembling. And those are on Stanford campus, Lockheed and Stanford people working hand in hand. Fine. So we're getting there. But there are a couple more things you've got to do, and one of them is you're going to eventually have to calibrate this gyroscope readout, because we're not measuring angles, we're measuring volts. And this is where what Fairbank used to call the anti-Murphy law comes into play. We all know what Murphy's law is, that something will go wrong if it can. The anti-Murphy law is really when you understand what you're doing, actually nature comes along and helps you. And nature injects a calibrating signal, the aberration of starlight, into your system and enables you to calibrate the gyroscope readout, because it moves the system around in a known way, and that appears in the output of the experiment. Okay, one of the great moments was when Brad Parkinson came on board to turn this into reality. And amongst the other things that he added is he told us all about GPS. This is 3 GPB GPS doctoral dissertations. And one of them was Clark Cohen's. I mean, it was obvious you'd better put a GPS receiver on so you have a real tracking of the spacecraft so you can calculate the relativity, the Einstein prediction. But Clark added three other GPS receivers. By the way, that's not the real scale, but that's taken out of his thesis. And realized that you could do orientation measurements, which led to this picture Andrew Barrow has also shown you, applying the same concept not only to the GPB spacecraft as part of its initial setup, but in other things. And then there are other theses from Jeff Creary, who looked at the possibility of it as the roll reference, and a very important thesis by Penina Axelred, which included, amongst other things, how we would like our injection accuracy to be. And this is a whole story of its own. This very remarkable man from industry, Don Davidson, who made many contributions, but including development of that telescope, which is a star tracker at the milliarc second level of accuracy. And there it is under test with an artificial star designed by Stanford students working with Dan DeBray. Fine. So meanwhile now we're getting to the close of being on orbit, and we've done a lot of thinking about all the errors in the experiment and how we calibrate them and everything. And this, which goes back to a Richard Vassar thesis with John Breakwell back in the early 1970s, is, though the particular curve shown is what Mac Kaiser had developed out of it, shows that you would expect the experiment to improve with time. Your first thought is it'll improve with time as t to the 3/2. Why? Because relativity goes up as time, noise should go down the square root of time, fit them together. It's a little more complicated than that because of aberration of the starlight, which is such a help, also alters the way in which it's done. Then there's a whole lot of error tree development and things, and I won't go into that, but you see again students involved all the way through. And finally comes the moment of truth when you're on orbit. And we wouldn't have been able to do this, I think, if we hadn't had the control station on the campus. There's some very good reasons for that. So there on the left is the spacecraft control with a mixture of Lockheed and Stanford and NASA people all looking at various things. Earlier you saw Rob Brumley at the far corner of that in one thing. And we have an anomaly room. You know, when you lose control of the spacecraft, the first thing you want to do is save the spacecraft. And the other thing you want to do is, what do we do next? The anomaly room separates those people so that you're not breathing down the necks of the people who are saving the spacecraft. We had about 25 students working with us in the control of the spacecraft over the time of it, including some summer students doing very interesting things. And now, finally, there's the in-flight verification. It took us longer to set up than we expected. Everybody told me that would happen, but it still took us longer. Then we went into a 353-day science phase, and then finally post-experiment test phase. And during this post-experiment test phase, we discovered some anomalies. We in particular discovered that there was a torque on the gyroscope that we hadn't expected. But before then, during the science phase, we had discovered another surprise. The pole hold rate was varying. By the way, Dan Debray and I had both proved that this could not happen. Nature wasn't listening. And these two surprises have been the reason why the data analysis, which is coming along remarkably well, took longer. So what you see here, probably everybody remembers pole hold motion, but the left-hand gyroscope began by spinning about its minimum moment of inertia, then turned over and went towards its through an intermediate and finally came down to a lower thing. But so that means the rotor was twisting around and the spin vector, and then another gyroscope. A couple of students there, San Diego and Solomon, were involved in this. And the problem with that is it complicates the calibrating of the gyro scale factor. The other thing was this discovered torque, which, as we pointed the gyroscope telescope off to a different star, we found that mispointing gave a much larger torque on the gyroscope. And you can easily see this as a torque. You point off by a certain angle, you get a drift. You double the angle, and you get twice the drift, and it's a torque because it's at right angles to the direction of mispointing. And these both originate in something we call the patch effect. Patch effect is contact potential differences, and it was one of the things that we weren't thinking about carefully enough, though we thought about it very intensively and made almost every relevant measurement. Almost every relevant measurement. Now, I'd love to go into the details, but I don't want to consume too much of your time. The problem of it is that the London moment story I've told you about is a little bit more complicated than it really is, because you get some trapped magnetic flux in the gyro rotor, and as the pole-hold period varies, we knew all about trap flux, but as the pole-hold period varies, the contribution of this to the magnetic moment also varies. And this means that because you do not get a fully accurate calibration in one orbit, but only by hooking together data from many orbits, you run into an issue. Here's some very wonderful work, however, from 3 graduate students, all aeroastro graduate students, where they solved the physics problem of mapping out the trap flux, determining the variation in the pole-hold phase over the course of an entire mission to within 2 degrees. This is incredible. Be able to hook together the data over the whole year to 2 degrees phase. Here's another little thing I just waved by you, which is during half the orbit, you're pointing with the guide star and measuring angles. During the other half of the orbit, you end up by using your science gyroscope to tell you what the pointing is. And that's cool. The red thing is when you're not seeing the star and not pointing at the star, you can still get out the angle, and this turns out to be important in the final calibration of the experiment. So, where do we stand? This is not fully final data. We've got very careful work looking into unmodeled things, but you see the GR prediction. You see for 85 days in the central part of the mission, at least what the statistical noise is. Do not yet take it as significant that that blue bob and the red bob don't coincide, but we are getting there. And in 85 days, if all the other systematics are properly under control, we're talking about measuring to 30%. Got to be very careful about all of what I'm saying here, but just to give you a feeling. And then you can think of that T to the 3 halves rule and more or less applying, and think about ending up with a completed measurement. So that's the data analysis team, a bunch of students here down in the bottom right-hand side. The team now is smaller than that, but that was what it was at its height, and these have been all people who have made major contributions. I'm glad to say John Conklin is still with us, and you can ask about him. Michael Dolphin and Michael Salomon have both graduated now. And how are we going to lock down the final result? Well, we're going to lock down the final result by completing this mapping of the trap flux so that we really get an accurate scale factor measurement. Then that helps a lot in sorting out the possible torque effects. And finally, we put together a post-flight error tree as a contrast to the pre-flight error tree, and it's coming along. This sort of is where we think we will end up with something like maybe a 3% measurement of the frame dragging effect, which has never been convincingly seen in any other way, and with that measurement of the geodetic effect, and a whole lot of work to do. And we're talking about the time scale. November the 8th, 008 is for the next step, then May, then September, and the final thing being ended March 2010. At which point we hope to have an engineering physics conference on what comes next. Yes.
Hello? Yeah, okay. I found your talk to be extremely interesting. There were basically, I think this whole project here served as a great example of a collaboration between government, which would be NASA, the academic community, which would be Stanford, and also the research labs of Lockheed in Palo Alto, which were right around the corner. And could you collaborate or discuss that in a little more detail about that collaboration between those basically three major groups?
I can, and I might like to ask Brad also to comment too. But you've missed out one of the most remarkable collaborations of all between a bunch of physicists and engineers at Stanford. Because I remember at a certain point a very senior person from MIT coming and asking us, how on earth can Stanford do this? We could never have done it at MIT. Maybe he was being modest, I don't know. But at one level, all it needs is goodwill and the fact that you actually need each other. At another level, it needs really understanding who the persons at the right level in the other organization whom you can trust are. And by trust, I don't mean necessarily simply honesty, though honesty is all important. It also means that they know what the issues are. You see, when you're working with a very different culture, which NASA is or industry is, you have to have somebody there who can continually give you insight into the culture. We've been very lucky at Marshall Center. Our final program manager, Rex Jeviden, by the way, who had a nice joke. His nice joke was that he and Gravity Probe B were conceived in the same year. He was exceedingly good at establishing the rapport and communication and figuring out, here's the things we can do at Marshall Center because our culture will allow us, and here's the things we can't do. So you have to figure out what you're going to do. And Brad, would you like to add comments?
Yeah, I would. Everyone hear me? I'd like to add something because, in modesty, Francis didn't mention this. I think it starts with leadership, that cooperation. And in case you didn't notice, this gentleman on my left gave great credit to everybody that was involved. And that's been a hallmark of what's happened. And I think not only does he give leadership, I think the other thing he did was give credit. And in my opinion, that was also a key. So thanks a lot.
Thank you.